Hi everyone, and welcome to this month's Tech Tuesday from the Toronto Local Network. Today's topic is a really interesting one on the $5 smart blood pressure system that was developed at University of Oxford. I'm going to switch straight across to our IET TV video so that we can get started.
So again, my name is Carlos Corteta, and I'm going to be presenting an affordable smartphone-based blood pressure smart system. It's going to work with Marco Pimentel, Mauro Santos, Joao Domingos, Mohamed Marassi, and the directors of the Oxford Center for Affordable Healthcare Technologies, Gary Clifford and David Clifton. I'll start by mentioning a few quick facts about non-communicable diseases. Well, we know they kill about 36 million people per year. The majority of these live actually in developing countries. And we also know that the management of non-communicable diseases is a long-term process that needs to happen effectively. Now, the particular non-communicable diseases that we're trying to target with this device is cardiovascular diseases. Specifically, we're trying to measure blood pressure and trying to target two of the critical steps for effective management of hypertension, and meaning early diagnosis and continuous monitoring. Now, we know that in order to do this management effectively in resource-poor setting, one of the issues that were discussed earlier also by Gary Clifford is the lack of, there are not enough trained personnel. And for that, previously, the World Health Organization has proposed a task shifting for the primary health care to happen, not necessarily in primary health care facilities, but by primary health care workers. And that's a great assumption. However, it does not come without additional challenges. And one specifically being the fact that how do you do this correctly using only a minimally trained personnel, right? So our solution for that, as seems to be kind of the subject of the theme of the day, is using mobile phones, of course. And what we're proposing here is this device that you're looking at the image. So now, what features this device has is, well, first of all, it only has some very minimal components. I'll tell you in a second specifically what it contains. So this is a very simple peripheral that is just going to connect. It's just going to turn essentially a normal blood pressure system into a smart blood pressure system by connecting a regular blood pressure cuff into a mobile phone. Now, all of the processing, all of the smart algorithms, all of the database storage, all of the data transmission, all of that is happening on the phone, and that actually allows us to keep the device extremely cheap. So as the talk is entitled, the $5 blood pressure system, that's actually referring to the estimated cost for mass production of that little box that is transforming this blood pressure cuff into a smart system. Now, what this device collects, as any other blood pressure device, collects systolic, diastolic blood pressures and heart rates. But actually, this one does one additional feature extraction, which is a respiration rate. And I will tell you in a second how we're actually managing to collect respiration rate out of this device. So what you see in the video is a colleague of ours using an older prototype, which is just as simple as that. The device is connected to the blood pressure cuff on one side. On the other side is connected via USB to the phone. So you can use the very good graphics in the phone to guide the user with very simple graphical instructions. So in this case, just pump, pump, pump until the system has recognized that pumping has been enough, and now stop pumping. It's just really as simple as that. Now, I have one with me here. It's not in a Tic-Tac box, but it's on a 3D printed box. And just come and see me afterwards if you want to have a close look at it. Now, what's inside of this device is really almost embarrassingly simple. It's just essentially a pressure sensor, which then takes two different paths. One of them is just being amplified and filtered. The other one is just the raw pressure signal, which is being sampled at 250 hertz with a resolution of 16 bits, and just sent via USB to a smartphone. And this is the type of signal that it will collect. So what you see in front of this line is just signal coming from the cuff. You can actually see there's little oscillations. And what you see in the background is the amplified and filter signal, which we refer to as the oscillometric signal. And from this signal is where the systolic and diastolic blood pressures are extracted, and actually the heart rate as well, just by doing a very simple frequency analysis of the oscillometric signal. Now, I also mentioned that this device collects respiration rates, and it's I suppose the question is why a blood pressure device would collect respiration rate. Well, respiration rate is actually another key vital sign. It is a very good indicator of illness, and however, regularly in clinical settings is either not measured or just measured by counting the chest movements over a period of 15 seconds or 30 seconds, and you multiply to make it over a minute. But actually, during the research for the development of this device, we realized we could actually extract this very easily from the oscillometric signal in a very similar fashion that's it's been done for ECG signals or pulse oximetry signals. So I'm just going to give you a brief idea of why this is possible. So it turns out that the oscillometric signal that I was describing before is modulated both in amplitude and in frequency by the respiration. So it turns out that due to changes in the thoracic pressure when you breathe, there is an amplitude modulation in the oscillometric signal. And also, let's say that depending on the stage of your breathing, either if you're inhaling or exhaling, the heart actually beats a little bit faster, a little bit slower. So that's the respiratory sinus arrhythmia. And you can actually see that as a frequency modulation on the oscillometric signal. So actually, I'm not going to go into the details of this, but it turns out that actually by doing this demodulation, both the amplitude demodulation and the frequency demodulation, we're able to extract respiration signals, which would look like this. For example, this is the demodulation of the amplitude modulated signal, and this is the modulation of the frequency one. Actually, there is a paper with all of the details of how to extract respiration rates from the oscillometric signal, which was presented a couple of weeks ago in the EMBC in the States. So I'm just going to refer you to that if you want to know details about how these computations are done. And I'm just going to jump into how we actually validated our device. So we ran a small trial in the university with 40 subjects, 65% of which were men, 35% women. And we actually did 2 sessions with these patients or volunteers. So the first session was in rest. So we would take all of the reference signals, and I'll tell you in a second what those were, while the person was sitting, relaxing. And the second session was in a bit of distress. So we actually asked our volunteers to squeeze like a stress ball part. So their respiration and their blood pressure and their heart rate was actually a little bit increased. We, as reference, we collected blood pressure measurements from other validated devices, in this case, a couple of Omron devices. We actually extracted as reference for respiration. We used the impedance plethysmograph, which is just the respiration band that you put on your chest, and this gives you a signal, looks like this. And also, for references for the heart rate, we collected the ECG of the volunteers. And essentially, the results were actually quite encouraging. We got for our blood pressure values, the majority of them, over 80%, were generally within the 0 to 5 millimeters of mercury difference. The majority, nearly 90% of the heart rate signals we collected were between 0 and 5 beats per minute difference in comparison to our references. And in the case of the respiratory rate, which is actually what we found most surprising, because it was kind of the most novel signal processing that we were doing on this device, we actually got differences. Over 80% of the cases, the respiration rate would actually manage to fit the reference signal with only a difference between 0 and 3 breaths per minute in over 80% of the cases. So these results were actually quite encouraging. And however, it does have a few considerations, and mainly, well, this was done on healthy volunteers, and nearly as a consequence of the limited range of values that we had was probably not ideal for a full trial, but this was our first in-house trial and was actually quite encouraging. So to finish, I'm just going to comment about what our efforts are trying to push this forward. We are actually at the moment partnering. We have a partnership with a company in the United States called Safe Heart. We're actually doing a medium-scale production of this device. So hopefully by next year we'll actually have a commercial product, if you will. Once we have our commercial products, we are going to start doing more larger scale validation, both for clinical use and say potential clinics and so on, and also for use in resource-poor settings. We're also doing research to extract additional features from the same signal that the device collects. One example can be the arterial stiffness. So you can start thinking of a device that is as cheap as that, but it still collects all of these clinical features that, when compared to commercial devices, you can only find in devices that are over 200 pounds or so. And we're also doing research on signal processing to actually increase the accuracy and sort of go away from the more traditional methods for computation of blood pressure. And well, if everything goes well, we'll actually be going for large production maybe towards the end of next year, hopefully with a partnership with Safe Heart. So right, so that's it for me. And again, I have the device with me. So if you want to see it in, if you want to have a close look, just come find me after the session, and I'll be happy to show it to you. Thank you.
Thanks. And again, if you haven't already connected with us on social media, please go ahead and do that so you can stay in touch and find out what else we have coming up, like our event this Friday at our holiday festive event, also on medical engineering theme, and some more activities coming up in the new year. And of course, thank you to IET TV for providing the content for today's webinar.